What James Webb found in the deepest darkness, where galaxies should be accumulating, upended everything. Ancient black holes burning in complete solitude. No fuel, no neighbors, just emptiness as it is. Scientists analyzed 20 years of cosmic measurements and discovered that we do not live in the universe we thought we did. We live inside a balloon approximately 2 billion light-years wide, within what is nearly nothingness. This void is growing and distorting everything we measure about reality. If you've liked and subscribed, let's begin the exploration. When the James Webb telescope focused on a region 13 billion light-years away, it encountered something that upended every model. 5 ancient quasars floating in cosmic deserts, blazing with the power of trillions of stars. These objects had formed when the universe was only 430 million years old. This timeline alone was virtually a challenge to physics. Quasars require supermassive black holes at their centers. Black holes, in turn, depend on matter, gas, dust, entire galaxies feeding the gravitational monster at the core. According to theory, these early quasars should have been situated in the densest neighborhoods of the young cosmos, surrounded by 50 or more companion galaxies fueling their fires. Scientists from MIT conducted this observation campaign in 2024. They examined the cosmic environment of each quasar field. Some matched the predictions perfectly, crowded environments filled with galactic neighbors, just as the models had anticipated. Then came the others. These quasars were drifting alone. Only a handful of stray galaxies were scattered nearby. There was no dense environment and no obvious fuel source either. Christina Alice and her team checked their data 3 times. The findings did not change. Solitary, supermassive black holes blazing impossibly in regions where they had no right to exist. This discovery was confirmed by multiple observations. The telescope's instruments captured clear images of these isolated regions. Every observation session revealed the same pattern. Dense quasar fields were expected. Empty quasar fields were impossible. This inconsistency pushed physicists to question fundamental assumptions about how black holes grow. Without matter in their surrounding environment to consume, these objects should have remained small. Instead, within a cosmic instant, they reached masses millions of times that of our own star. The location of these solitary quasars pointed to something stranger than random distribution. They existed within voids, vast regions of space with below-average matter density. It was known that voids existed in the modern universe. Finding them in the infant cosmos, already large enough to isolate quasars, contradicted the timelines of structure formation. The universe at that age should have been more homogeneous. Gravity had not yet pulled matter into the extreme concentrations and rarefactions we observe today. The team published their findings in the Astrophysical Journal in October 2024. The results were cautious but clear. These quasars exist in environments that current theory cannot explain. Either black hole growth operates through unknown mechanisms, or the early universe harbored structure at scales previously thought impossible. Either possibility was enough to rewrite the cosmology textbooks. And neither was reassuring, because what Webb found at the edge of the observable universe may also exist in this region surrounding our own galaxy. Our home galaxy is drifting inside a nearly empty bubble of space, 2 billion light-years wide. The KBC void, named after the 3 astronomers who first identified it in 2013, wraps around the Milky Way like an invisible sphere. This structure was confirmed by galaxy counts conducted across multiple wavelengths. Optical telescopes, infrared surveys, X-ray observations, radio measurements all point to the same conclusion. Our local universe contains 20% less matter than it should. Imagine the cosmos as an ocean. Galaxies cluster into islands and archipelagos connected by bridges of matter. These structures formed the cosmic web, a network spreading across the entire observable universe. Between the dense filaments stretch voids, like open waters between chains of islands. The vast majority of galaxies live on the islands or the bridges. We, however, live in the middle of the ocean. The KBC void is not the only empty region in space. Thousands of voids have been mapped, but this one is different. It is among the largest ever detected. More importantly, we are located at a point close to its center. This discovery emerged from near-infrared surveys counting galaxies at increasingly greater distances from Earth. The density of nearby galaxies appeared normal, but as astronomers extended their surveys further to 200 million light-years, then 400 million, then 600 million, something became clear. The number of galaxies per unit volume increased steadily with distance. We live in a region of significantly below average density compared to the cosmic mean.
The deeper space telescopes looked, the more pronounced the inconsistency became. This finding was confirmed by multiple independent research teams using different methods. The two-mass redshift survey cataloged more than 43,000 galaxies within 380 million light-years. The pattern held: fewer galaxies nearby, more farther away. This distribution matched the predictions of an observer situated inside a supervoid. Additional observations from the Sloan Digital Sky Survey and the WISE infrared mission reinforced the result. Our cosmic neighborhood is genuinely sparse. The void overlaps with the Laniakea supercluster, which hosts 100,000 galaxies, including the Milky Way. This appears contradictory at first glance. How can a supercluster exist inside a void? The answer lies in scale. Laniakea stretches across 500 million light-years. The KBC void, however, spans 2 billion. The supercluster represents a relatively dense region within a volume of overall low density, much like a small island in the middle of the Pacific, still surrounded by vastness, still fundamentally alone. The implications of this location extend far beyond simple geography. Living inside a void changes how we measure the universe itself. Two groups of astronomers are measuring the same thing and obtaining results that do not match in any way. The Hubble constant defines how fast the universe is expanding. It gives the rate at which space itself is stretching and carrying galaxies away from one another. This number is not optional in cosmology. It determines the age of the universe, the distribution of dark energy, the timeline of cosmic evolution. Everything depends on getting this number right. But the measurement methods keep returning conflicting values. The deeper space telescopes looked, the more pronounced the inconsistency became. This finding was confirmed by multiple independent research teams using different methods. The two-mass redshift survey cataloged more than 43,000 galaxies within 380 million light-years. The pattern held: fewer galaxies nearby, more farther away. This distribution matched the predictions of an observer situated inside a supervoid. Additional observations from the Sloan Digital Sky Survey and the WISE infrared mission reinforced the result. Our cosmic neighborhood is genuinely sparse. The void overlaps with the Laniakea supercluster, which hosts 100,000 galaxies, including the Milky Way. This appears contradictory at first glance. How can a supercluster exist inside a void? The answer lies in scale. Laniakea stretches across 500 million light-years. The KBC void, however, spans 2 billion. The supercluster represents a relatively dense region within a volume of overall low density, much like a small island in the middle of the Pacific, still surrounded by vastness, still fundamentally alone. The implications of this location extend far beyond simple geography. Living inside a void changes how we measure the universe itself. Two groups of astronomers are measuring the same thing and obtaining results that do not match in any way. The Hubble constant defines how fast the universe is expanding. It gives the rate at which space itself is stretching and carrying galaxies away from one another. This number is not optional in cosmology. It determines the age of the universe, the distribution of dark energy, the timeline of cosmic evolution. Everything depends on getting this number right. But the measurement methods keep returning conflicting values. The first approach examines the cosmic microwave background radiation, ancient light from 380,000 years after the Big Bang. This radiation carries imprints of the infant universe as patterns frozen into the sky at the moment atoms first formed. Detailed analysis of these temperature fluctuations reveals an expansion rate of approximately 67 kilometers per megaparsec per second. The Planck satellite measured this value with extraordinary precision, and it aligns almost perfectly with the standard model of cosmology. The second method examines nearby galaxies. Astronomers identify Cepheid variable stars, which pulsate predictably according to their true brightness. By comparing apparent brightness to true brightness, distances can be calculated. These distance measurements extend all the way to galaxies that host Type 1a supernova explosions, which serve as standard candles at cosmic distances. This local measurement technique, refined by Adam Rees and his team using both Hubble and Webb data, returns a different answer, approximately 73 kilometers per megaparsec. That is 10% higher than the microwave background method. 10% may sound modest. In cosmology, it signals a crisis. The tension grew larger as measurements improved. In early observations, margins of error left room for overlap. Modern precision eliminated that comfort. Both techniques were checked, rechecked, and verified with independent observations. The Webb telescope confirmed the distance ladder measurements that Hubble had initiated. Systematic errors could not account for the discrepancy. Instrument calibration issues did not resolve the contradiction. The numbers simply refused to agree. This inconsistency has persisted for more than a decade. Nobel laureate Rees noted that as measurements became more precise, the tension did not disappear. On the contrary, it deepened. If the local measurements are correct, the universe may be approximately 1 billion years younger than current calculations suggest. Galaxy formation timelines would change, dark energy behavior would differ. The entire structure of cosmic history would have to be reorganized. If instead the cosmic microwave background measurements are correct, then there is something unknown in our local region that is accelerating expansion and affecting all nearby distance measurements. In either case, our understanding of the universe contains a fundamental flaw. But what if the answer does not lie in our measurements? What if the answer comes from where we are measuring? Before atoms existed, the universe was a screaming plasma of particles and energy. Photons, electrons, protons, and dark matter were churning together in a hot fluid, along with pressure waves generated by tiny density fluctuations arising from quantum events in the first moments of creation. These waves traveled at roughly half the speed of light, compressing matter as they propagated. Then, 380,000 years after the Big Bang, everything changed. The universe cooled enough for electrons and protons to combine and form hydrogen atoms. Light was set free. The waves froze in place. These frozen sound waves left their traces in two places.
First, in the cosmic microwave background radiation itself, visible as subtle temperature differences across the sky. Second, and more importantly for void detection, in the distribution of matter throughout space. The regions where the waves had compressed matter became slightly denser. These overdense regions drew in more matter through gravity over billions of years, eventually forming the galaxy clusters and filaments we observe today.
The distance between the compressed regions, approximately 490 million light-years in today's expanded universe, became a cosmic ruler. Astronomers call this baryon acoustic oscillations. This cosmic ruler works because the distance is fixed by physics. Sound waves could only travel a certain distance in the time before atoms formed. This maximum distance, called the sound horizon, provides a standard length scale imprinted across the entire universe. By measuring how large this scale appears in galaxy surveys at different distances, cosmologists can determine both how far away those galaxies are and how fast space was expanding at different points in cosmic history. The Dark Energy Spectroscopic Instrument, or DESI, is conducting the most detailed surveys of these oscillation patterns. The telescope measures the positions and redshift values of millions of galaxies. Redshift shows how much space has expanded since light left a galaxy and provides a distance measurement. When plotted, galaxies show a faint preference for certain distances at multiples of that 490 million light-year scale. The pattern remains ambiguous in small samples, but emerges clearly when millions of galaxies are analyzed together. Recent DESI observations revealed something unexpected. Baryon acoustic oscillation measurements do not align perfectly with the predictions of the standard cosmology model. At low redshifts, that is, at closer distances, the apparent expansion rate exceeds expectations. At high redshifts, at greater distances, the measurements fall in line with cosmic microwave background predictions. Something is creating a systematic shift in nearby observations.
Data published in 2025 showed this deviation concentrated within specific redshift intervals. Two particular distance ranges accounted for the bulk of the anomaly. Cosmologists proposed various explanations: dark energy varying over time, modified gravity, unknown systematic errors in the surveys. But there was another possibility that few wanted to consider. What if the measurements are correct and we simply live in a special place? Scientists from the University of Bonn and the University of St. Andrews compiled 20 years of baryon acoustic oscillation data. They modeled what these measurements would look like if Earth were located inside a large, low-density region. They then compared these predictions against real observations. The results were not modest. Models incorporating a local void matched the data 100 million times better than models assuming a uniform matter distribution. This finding was confirmed by a rigorous statistical analysis published in the monthly notices of the Royal Astronomical Society in 2025. The analysis focused on a specific measurement called d sub v, which combines angular and radial measurements in a particular way. In a perfectly uniform universe expanding according to standard cosmology, this quantity should follow a smooth curve as observers look to greater distances. The compiled observations show something different. At redshifts below 0.3, corresponding roughly to distances within 4 billion light-years, the measurements deviate systematically from predictions. The observed d sub v values appear larger than expected. This is precisely the pattern a local void would create.
The mechanism operates through gravitational dynamics. Inside a low-density region, matter feels a pull toward the denser material outside. This creates bulk flows in which galaxies move away from the void's center faster than pure cosmic expansion could push them. These peculiar velocities add on to the cosmological redshift.
When astronomers observe a galaxy and measure its redshift, they assume all of its motion stems from the expansion of space. If the galaxy carries an additional outward velocity from void flows, its redshift appears slightly higher. This inflates distance estimates. The researchers tested 3 different density profiles for the void: the Maxwell-Boltzmann distribution, the Gaussian distribution, and the exponential distribution. All 3 improved the fit compared to the void-free model. Statistically speaking, the uniform model is about as likely as getting tails 13 times in a row. The void model is about as likely as getting tails twice in a row, a significant difference. A separate analysis examined how quickly the apparent cosmology returns to standard predictions at high redshifts. Any local solution to the Hubble tension must eventually yield to global behavior as observations extend well beyond the void. The model predictions show precisely this transition. At low redshift, where void dynamics dominate, expansion appears faster. At high redshift, beyond the void's influence, measurements fall in line with cosmic microwave background expectations. But the statistics do not tell the full story. Physical evidence from galaxy motions confirms the void through much more direct means. Galaxies inside low-density regions move differently from their counterparts in normal space. The Milky Way itself is moving away from the void's center at 600,000 miles per hour. This peculiar velocity, confirmed by measurements of our motion relative to the cosmic microwave background, far exceeds typical galaxy speeds in denser environments.
The void is not pushing us. The matter outside is pulling. Gravity from the surrounding filaments and superclusters creates a net force drawing everything outward from within the void. This phenomenon is called bulk flow. Astronomers measure it by observing many galaxies within a spherical volume centered on our location and calculating their average velocities. The Cosmic Flows project catalogs these motions using various distance measurement techniques. The 4th version of this catalog, published in 2023, contains redshift-independent distances for thousands of galaxies. Analyzed together, they reveal that the Milky Way is participating in a large-scale flow motion. The observed bulk flow curve rises with distance out to approximately 250 megaparsecs and reaches speeds roughly 4 times higher than what standard cosmology models predict. Serge Mazzareno and colleagues demonstrated in 2024 that void models naturally explain this behavior. Matter flowing outward from a low-density region maintains consistent motion across enormous volumes. The KBC void parameters that fit the Hubble tension also predict bulk flows that align with observations. The velocity field displays distinctive characteristics tied to the void's geometry. Galaxies near the void's center move outward in every direction. As distance from the center increases, outflow velocities decrease. Eventually, at the void's boundary, approximately 1 billion light-years away, the expansion rate returns to the cosmic average. Beyond this point, gravity from denser regions takes over.
The transition zone, where void dynamics fade, creates complex patterns of motion. Some galaxies are accelerating toward nearby attractors, such as the Shapley concentration. Others are fleeing relative voids like the dipole repeller. Our location is experiencing both effects simultaneously. The local sheet, a flattened distribution of galaxies that includes the Milky Way, represents a wall of a smaller void structure nested within the larger KBC void. This smaller void, sometimes called the local void, stretches approximately 200 million light-years and sits adjacent to our location. Galaxies in the local sheet are moving away from its center at 160 kilometers per second. The effect resembles water draining from a basin. Matter flows preferentially out of voids and accumulates along their boundaries, becoming the sheets and filaments of the cosmic web. We have made our home in one of these transition zones and are witnessing cosmic drainage in real time. The forces that shaped us, however, reach all the way back to the first moments after creation. 13 billion years ago, when starlight first ignited in the primordial darkness, something was already feeding. Supermassive black holes existed less than 1 billion years after the Big Bang. The Webb telescope detected several whose masses exceed 1 billion times that of our own star. A quasar examined by the Aspire program outshines its entire host galaxy despite existing only 830 million years after creation. This timeline presents a devastating problem for theory.
Black holes grow by consuming matter. Standard growth models involve 2 stages. First, a seed black hole forms from the collapse of a massive early star, beginning with a mass perhaps 100 times that of our own star. The seed then accumulates gas from its surroundings over time. But accretion has limits. Matter falling into the black hole heats up and radiates energy. This radiation pushes back against the infalling matter, creating a natural throttle on the rate of growth. Even under the best conditions, a black hole can only double its mass every 50 million years through this process. Run the numbers backward. A black hole of 1 billion solar masses detected 800 million years after the Big Bang had only that much time to grow. Starting from a seed of 100 solar masses requires the mass to double 20 times. At maximum accretion rate, 20 doublings take 1 billion years. The timeline does not fit. These objects reached their observed masses faster than physics should allow through conventional feeding. Something else happened. 2 possibilities stand out. Either seed black holes began far more massive than stellar collapse can produce, or they grew through mechanisms beyond standard accretion. The first scenario involves direct collapse black holes. Under rare conditions in the early universe, large primordial hydrogen clouds may have collapsed directly into black holes without first forming stars. This process could produce seeds of between 10,000 and 1 million solar masses, a significant head start. The second scenario involves super Eddington accretion, in which black holes consume matter faster than radiation pressure should allow. Both mechanisms remain theoretical. Neither has been confirmed by direct observation.
Roberto Maialino's team using Webb found additional evidence pointing to unusual black hole growth. Near these early quasars, they detected extremely dense gas consistent with rapid accretion. They also observed powerful winds being ejected from the systems at enormous speeds. This combination points to violent and chaotic feeding processes that carry matter away from the black hole, while other matter falls in. The quasars appear to be growing in desperate bursts, consuming whatever fuel exists in their sparse surroundings. Some scientists propose that these objects inhabited regions that would go on to become the voids we observe today. Early high densities permitting rapid black hole formation, followed by the expansion and drainage of surrounding matter. Testing this hypothesis requires understanding how voids form in the first place. The KBC void contains galaxies, stars, dark matter, and ordinary matter. It is not a true vacuum. The term void describes relative density, not absolute emptiness. According to some studies, the matter concentration within the void is approximately 80% of the cosmic average. Other analyses point to densities as low as 50% of the average. All measurements agree on one point: our region is significantly below average in density compared to typical cosmic neighborhoods. This 20% matter deficit produces enormous consequences.
Gravity weakens in low-density regions. With less mass pulling inward, the expansion of space meets less resistance. Imagine one person inflating a balloon with heavy weights hanging from its surface, while another inflates one with nearly weightless threads barely pulling at all.
The balloon stretches faster where resistance is weakest. The universe behaves similarly. Regions below average matter density expand slightly faster than average, while regions above average expand slightly slower. The effect accumulates over cosmic time. For observers inside a low-density region, this creates a systematic bias in measurements. When astronomers calculate the Hubble constant using local galaxies, they are sampling an environment that is expanding faster than the global average. The measured expansion rate appears elevated. This explains why local measurements using Cepheid stars and supernovae return higher values than cosmic microwave background predictions. Both measurements are correct, they are simply examining different environments. The cosmic microwave background reveals the global average expansion, while local measurements reflect the expansion at our peculiar location. The mechanism has been confirmed by multiple lines of evidence. Computer simulations of structure formation in the universe naturally produce voids with characteristics similar to the KBC void. These simulations begin from initial conditions that align with cosmic microwave background observations and proceed using known physics. Voids emerge as inevitable features of gravitational structure formation. Matter comes together and clusters under its own gravity, leaving behind drained regions. Simulations estimate that voids occupy approximately 70% of the universe's volume, despite hosting only a small fraction of its galaxies.
Observations of distant quasars gravitationally lensed by foreground matter distributions provide another test. Lensing power depends on the total mass along the line of sight between the observer and the quasar. Studies found that some lines of sight show below-average lensing, consistent with passing through low-density regions. The distribution of lensing powers across the sky aligns with the predictions of large-scale structure surveys, showing networks of voids and filaments. We are not special in living near a void. What makes ours special is how large this void is and how it affects the way we perceive cosmic reality. To understand what fills the luminous regions, one must look to this structure spanning 500 million light-years and hosting 100,000 galaxies. The Milky Way occupies a small corner of this structure called Laniakea, a word meaning immeasurable heaven in Hawaiian. Laniakea encompasses the Virgo supercluster, the Hydra Centaurus supercluster, and the Pavo Indus filament. All of these galaxies share a common motion, flowing together toward a shared gravitational basin of attraction. Detailed surveys published by Brent Tully and colleagues mapping this structure revealed the boundaries of Laniakea in 2014. The discovery began to establish our cosmic neighborhood as a principal feature of the universe. Then came the realization that changed the interpretation. Laniakea lies within the KBC void. The supercluster in its entirety, with all its galaxies and matter, occupies a region of space that is broadly low in density. This creates a paradoxical situation. How can a massive concentration of galaxies exist inside a void? The answer lies in scale and context. Laniakea represents the densest region within a broader low-density expanse. Think of it as a mountain peak in a valley. It rises above its immediate surroundings, but remains lower than the peaks in adjacent mountain ranges. The void does not eliminate structure. It suppresses average density across enormous volumes. Gravitational dynamics within Laniakea reflect the void's influence. Galaxies flow toward the Great Attractor, a mass concentration near the center of Laniakea. At the same time, the supercluster as a whole participates in the outward flow from the KBC void's center. These motions combine. Our galaxy is moving toward the Shapley concentration, a massive galaxy cluster beyond the edge of Laniakea. We are also moving away from the dipole repeller, a low-density region on the opposite side of the sky. The repeller does not push, it simply cannot pull as strongly as the matter surrounding it. The combined effect creates our peculiar velocity through space.
Recent analyses suggest that Laniakea may not be gravitationally bound. The outward flow from the void may overcome the supercluster's internal gravity and prevent it from collapsing into a single structure. If true, Laniakea is a transient feature. The galaxies that appear together today will disperse as the void continues to expand. This calls into question the idea that superclusters form stable, long-lived structures. They may be temporary concentrations within larger drainage flows.
The void's influence extends beyond motion and affects galaxy properties as well. Studies comparing void galaxies with their counterparts in denser regions found systematic differences. Void galaxies tend to be smaller, bluer, and younger. They form stars more actively despite having less available gas. This phenomenon has been confirmed across multiple void examples throughout the universe. The explanation involves environmental effects. In dense regions, galaxies frequently interact and merge. These violent encounters can halt star formation when gas is heated or ejected. In voids, galaxies evolve in relative isolation, retaining their gas reserves for longer and continuing to form stars at a steady rate. Our location in a low-density region may have influenced the evolutionary history of the Milky Way, and the forces that created our void have been shaping the cosmos since the very first second of creation. In the beginning, space was nearly perfectly flat. During cosmic inflation, quantum fluctuations produced tiny density variations, 1 part in 100,000. Regions of slightly above average density contained slightly more matter. Those slightly below contained slightly less. These differences, microscopic at first, carried the seeds of all future structure. Gravity amplified the differences. Dense regions attracted more matter and grew denser. Low-density regions lost matter to their surroundings and emptied further. The process fed itself over billions of years. The timeline of void growth follows the history of cosmic expansion. In the first few 100 million years, matter remained relatively evenly distributed. The universe had not yet expanded enough for gravitational instability to produce extreme density contrasts. Small voids existed, but remained shallow. Then stars and galaxies began forming in the overdense regions. These concentrations exerted stronger gravitational pull on their surroundings. Matter accelerated toward them, draining the low-density regions more rapidly. Voids deepened and widened. The contrast between dense and empty grew more pronounced.
Dark energy altered void evolution approximately 6 billion years ago. Before that transition, matter dominated cosmic dynamics. Gravity was slowing expansion everywhere, though less effectively in dense regions than elsewhere. Once dark energy became the dominant factor, expansion accelerated. This acceleration affected low-density regions more strongly than dense ones. Where matter concentration was high, local gravity partially counteracted dark energy's push. Where it was low, dark energy drove expansion with less resistance. Voids began inflating faster, their boundaries thrust outward into the surrounding space. The local void illustrates this process on a smaller scale. It stretches approximately 200 million light-years and sits adjacent to the Milky Way. The galaxies forming the local sheet, including our own, are moving away from this void at 160 kilometers per second. This speed exceeds what pure cosmic expansion could produce at these distances. The extra motion comes from the gravitational repulsive effect. Low-density regions create negative pressure gradients. Matter feels a net force pushing it away from the void center, as though being pushed by invisible hands. In reality, matter is simply falling toward the denser regions surrounding the void, but the effect resembles an active launching. Computer simulations tracking void evolution show that they grow primarily through evacuation rather than expansion.
As galaxies move toward dense filaments and clusters, they leave behind increasingly sparse regions. Void volume grows as matter redistributes. Eventually, voids reach a characteristic size determined by the balance between gravitational infall and cosmic expansion. The largest voids stretch across a few hundred million light-years. The 2 billion light-year KBC void strains or exceeds this typical scale. Some researchers question whether a void of this size could form within standard cosmology. Alternative theories proposing modified gravity argue that structure formed faster than conventional models predict, allowing extreme voids to develop.
But regardless of the formation mechanism, the void surrounding us shapes our observations in profound ways, including phenomena we may never be able to observe at all. Imagine the universe as a frozen foam. Dense walls surround empty bubbles. Where the walls intersect, thick filaments form. Where the filaments converge, enormous nodal accumulations gather. This structure, called the cosmic web, organizes all matter across billions of light-years. The walls contain galaxy sheets. The filaments contain galaxy groups. The nodes contain galaxy clusters. The bubbles are voids. Each component plays its own distinct role in cosmic dynamics. Together, they form a pattern that resembles neural networks or biological tissue at impossible scales. Galaxy filaments are among the largest known structures. Individual filaments can stretch 300 million light-years or more. The Sloan Great Wall, discovered in 2003, is 1.4 billion light-years long. The Hercules Corona Borealis Great Wall may extend up to 10 billion light-years, though its status as a single coherent structure remains disputed. These filaments are not solid objects. They consist of galaxy clusters and groups connected by diffuse gas threads. Matter concentrates along these highways, much like cities along ancient trade routes. Traffic flows through the web as galaxies fall toward massive clusters along the filaments.
Walls form where filaments intersect, creating two-dimensional galaxy sheets. The local sheet displays this feature, hosting the Milky Way, Andromeda, and hundreds of other galaxies spread across a flattened distribution. Walls are typically 100 to 300 million light-years wide, but only 10 to 30 million light-years thick. Like panels of a foam structure, they separate adjacent voids from one another. The vast majority of galaxies in the universe live not in clusters or voids, but in walls and filaments. These intermediate density environments host ongoing star formation and represent the typical galactic habitat. Voids fill the spaces between walls and filaments. They occupy approximately 70% of the universe's volume, yet contain only a small fraction of its galaxies. Typical voids stretch 30 to 100 million light-years. Supervoids exceed 300 million light-years. The Boötes void, discovered in 1981, stretches 330 million light-years and hosts only approximately 60 galaxies. For comparison, a similar volume of cosmic space would typically contain around 2,000 galaxies. The void is deep but not absolute. Recent surveys have revealed even larger structures. Baryon acoustic oscillation features create periodic clustering patterns at scales approaching the 490 million light-year scale of the sound horizon. Some apparent structures may represent statistical fluctuations rather than physically bound systems. Debate continues over what constitutes a single structure and what represents multiple features from overlapping regions that happen to be aligned by chance. What remains beyond dispute is the universe's organization at extreme scales. Gravity has carved space into a web of full and empty, light and dark. We live in one particular bubble of this foam, witnessing cosmic drainage in real time. And our peculiar location affects not only what we can see, but also what we may never be able to observe at all. The universe is 13.8 billion years old, or approximately 10% younger. The age calculation depends on the Hubble constant. Higher expansion rates mean the universe reached its current size in less time. If local measurements showing faster expansion are correct, without accounting for void effects, the cosmic age drops to approximately 12.5 billion years. This creates a devastating problem. Astronomers have detected stars older than that. Globular clusters host some of the most ancient stars in the universe. Detailed analysis of their light reveals that the oldest examples have ages exceeding 13 billion years. These measurements come from an understanding of stellar evolution. Stars burn fuel at predictable rates according to their mass and composition. As they age, their surface temperatures and luminosities follow known patterns. By comparing observations against theoretical models, astronomers can determine ages with reasonable precision. The margin of error allows some flexibility, but not enough to fit these stars into a 12.5 billion-year-old universe. If local expansion measurements are correct at face value, either stellar age calculations are fundamentally wrong, or the universe is older than its expansion history suggests. The first possibility seems unlikely, given how well stellar models align with other observations. The second makes no sense at all. A universe cannot be younger than its contents. This paradox makes a re-examination of assumptions necessary. The void hypothesis resolves this tension without requiring exotic physics. It proposes that local expansion measurements reflect local conditions within a low-density region rather than global cosmic history. This framework is consistent with both cosmic microwave background observations and stellar ages.
The solution works because age calculations require an integration over cosmic history. Astronomers model how fast the universe was expanding at different periods and sum up the time. In standard cosmology, this calculation uses a single expansion rate valid everywhere. In void cosmology, different regions expand at different rates. The global average expansion aligns with cosmic microwave background predictions. Local expansion inside voids proceeds faster. Both propositions can be true simultaneously. Our measurements capture locally enhanced expansion. The age of the universe, however, reflects the global average. This framework explains the Hubble tension while preserving the successes of standard cosmology. The cosmic microwave background, the abundance of primordial elements, the observed large-scale structure, all remain consistent with their current interpretations. Only the local distance ladder measurements require reinterpretation as tools measuring the void environment rather than global cosmology. The elegance of this solution appeals to many researchers. It resolves multiple problems without requiring new physics or exotic components. But elegance does not mean correctness. Alternative explanations for the Hubble tension propose modifications to fundamental laws. General relativity has passed every test for more than 100 years. From Mercury's orbit to gravitational waves, Einstein's theory predicts observations with striking accuracy. Yet explaining the universe we observe still requires dark matter and dark energy. 85% of matter must be invisible, and 70% of cosmic energy must be a mysterious field driving accelerated expansion. Some physicists wonder whether, rather than inventing invisible components, we may be missing something fundamental about gravity itself.
Modified Newtonian dynamics, proposed by Mordechai Milgram in 1983, changes how gravity operates at low accelerations. In regions where gravitational forces are extremely weak, the theory predicts that gravity remains stronger than Newton or Einstein would anticipate.
This modification eliminates the need for dark matter in galaxies. Galaxy rotation curves, which standard physics explains through dark matter halos, emerge naturally from the modified force law. The theory also produces testable predictions about galaxy behavior that align with observations in many cases. Applying these modified dynamics to cosmology, modified Newtonian dynamics proposed by Mordechai Milgram in 1983 changes how gravity operates at low accelerations. In regions where gravitational forces are extremely weak, the theory predicts that gravity remains stronger than Newton or Einstein would anticipate. This modification eliminates the need for dark matter in galaxies. Galaxy rotation curves, which standard physics explains through dark matter halos, emerge naturally from the modified force law. The theory also produces testable predictions about galaxy behavior that align with observations in many cases. Applying these modified dynamics to cosmology requires additional components. Pavel Krupa and colleagues developed a framework called NUHDM, which combines modified gravity with sterile neutrinos as a warm dark matter component. The rest energy of the sterile neutrinos is approximately 11 electron volts. They interact weakly with ordinary matter but contribute to cosmic evolution. This hybrid model reproduces cosmic microwave background observations while enhancing structure growth at scales above 100 megaparsecs. Critically, it allows larger voids to form earlier in cosmic history than standard cosmology permits. Indranil Banik and colleagues demonstrated in 2020 that modified gravity naturally produces the KBC void with its observed characteristics. Their simulations began from cosmic microwave background initial conditions and evolved forward using the modified force law. Voids formed faster and developed more deeply compared to standard gravity simulations. The resulting structure aligned with galaxy surveys, showing local underdensity. The same models also predicted bulk flow velocities consistent with cosmic flows observations. Without modified dynamics, producing a void as large as the KBC in a universe governed by Einstein's equations appears extremely difficult. Multiple studies suggest the probability of such a structure existing within standard cosmology is below 1%. The debate remains unresolved. Modified gravity theories also struggle with their own challenges. They have difficulty explaining certain gravitational lensing observations where light bending appears stronger than modified dynamics predict. The bullet cluster, where two galaxy clusters collided, displays a separation between visible matter and gravitational lensing that aligns better with dark matter explanations than with modified gravity. Proponents argue these systems require additional physics beyond the core modified theory. Critics regard these corrections as just as much of a patch as adding dark matter itself.
The one point both sides agree on is this: there is something we fundamentally misunderstand about either the composition of the universe or the behavior of gravity. The void surrounding us may hold clues as to which. Detecting underdensity at your own location presents a unique challenge. Astronomers cannot step outside the universe and look back at where we are. All observations must be made from within the structure being examined. This creates systematic blind spots. Measuring local galaxy density requires comparison with the cosmic average density. Determining the cosmic average requires surveying large volumes. Surveys conducted from within a low-density region will initially sample predominantly low-density space. Noticing the inconsistency requires reaching far enough to step outside the local effects. Early galaxy surveys lacked the depth needed to reveal the void. The Harvard Center for Astrophysics Redshift Survey of the 1980s cataloged galaxies within a few hundred million light-years. This pioneering work discovered cosmic structures, including smaller voids and filaments. It revealed that galaxies are not evenly distributed, but cluster together, forming patterns. However, its limited reach prevented recognition of the much larger KBC void.
Detecting a 2 billion light-year structure requires observing well beyond its boundaries. Surveys reaching only 300 to 400 million light-years are sampling predominantly the interior of the void. The breakthrough came from near-infrared observations. The 2-micron all-sky survey, or 2MASS, mapped galaxies at wavelengths where dust obscuration is minimal. This allowed penetration into sky regions where optical surveys struggled. The 2MASS redshift survey extended this by measuring distances to more than 43,000 2MASS galaxies. The published data reached approximately 380 million light-years. The 2013 analysis by Keenan, Barger, and Cowie revealed the critical pattern. Galaxy number density increased systematically with distance from Earth. The finding was initially met with skepticism. Could the pattern represent a selection effect or a systematic error in the survey? Subsequent analyses using independent datasets confirmed the result. Observations at other wavelengths, including optical, X-ray, and radio, consistently showed low density. The Sloan Digital Sky Survey, which mapped millions of galaxies across wide areas of sky, supported the result when specifically analyzed for local density.
By 2017, multiple independent teams were in agreement. Earth's cosmic neighborhood is genuinely low in density compared to typical regions of the universe. Even after confirmation, interpreting its significance took time. Early publications focused solely on characterizing the void structure. Connecting it to the Hubble tension emerged gradually as the expansion rate discrepancy became more apparent as measurements grew more precise. The realization that our peculiar location might explain cosmology's greatest puzzle has only gained attention in the last few years. The void was hidden in plain sight, not because of any unique property of the void itself, but because of the difficulty of noticing the abnormality of your own location when there is no possibility of observing from anywhere else. And the existence of the void traces all the way back to patterns frozen into space in the very first moments of creation. In the trillionth of a trillionth of a trillionth of a second after the Big Bang, quantum fluctuations rippled through the inflating universe. These fluctuations, arising from fundamental uncertainty in quantum fields, created tiny variations in energy density. Inflation, the rapid exponential expansion of space during a small fraction of the universe's first second, stretched these microscopic quantum fluctuations to cosmic distances. When inflation ended, the fluctuations were spread across millions of light-years, providing the seeds for all subsequent structure formation. The pattern of these primordial fluctuations appears in cosmic microwave background observations. The Planck satellite mapped temperature variations across the sky to a precision of 1/1,000,000th of a degree. Hotspots correspond to slightly denser regions in the early universe, cold spots to slightly sparser ones. The statistical properties of these variations align with predictions from quantum field theory during inflation. The amplitude of the fluctuations, the spectrum of sizes, the slight deviation from perfect randomness, all are consistent with theoretical expectations. This alignment ranks among the most successful predictions in physics.
From these initial density differences, gravity carved out the universe as it exists today. Overdense regions drew in surrounding matter. As matter flowed inward, these regions grew denser still, and the process accelerated. Small density enhancements led to the first protogalaxies, protogalaxies to galaxies, galaxies to groups, groups to clusters, clusters to filaments, and filaments framed the voids. The entire cosmic web emerged from the amplification of quantum noise stretched to astronomical scales. Low-density regions underwent the opposite evolution. Beginning with a slightly below-average density, they lost matter to their surroundings. As matter drained away, local density fell further below the average. The process created expanding bubbles of relative emptiness. The earliest voids were shallow. They deepened over billions of years as matter continued to drain.
The largest voids trace back to the largest initial underdensities in the primordial quantum fluctuation field. In the early universe, these rare extreme deviations grew into the supervoids we observe today. The existence of the KBC void points to an unusually large underdensity in the quantum fluctuation field overlapping our location. In a statistically large enough universe, features of this kind must exist somewhere. The question is whether finding ourselves in such a place is surprising. Some researchers argue that it is not. The universe extends far beyond our observable region, and extreme fluctuations must arise somewhere. We simply observe from where we are. Others suggest that the void's size strains or exceeds what standard inflation models can naturally produce. If true, this might indicate either that inflation operated somewhat differently from what current theory describes, or that it simply represents a rare but possible fluctuation. In either case, the void surrounding our galaxy began as quantum uncertainty at the smallest scales, was stretched to cosmic dimensions by inflation, and was amplified by billions of years of gravitational evolution, and its unceasing growth is tied to the most mysterious component of the universe.
According to current observations, dark energy constitutes 68% of the universe's total energy density. Unlike gravitationally attractive matter, dark energy drives cosmic expansion. The current standard model treats dark energy as a cosmological constant, a uniform energy density filling all of space. This simple model aligns with the vast majority of observations. Nevertheless, the effect of dark energy on structure formation varies by environment. In regions where matter concentration is dominant, gravity suppresses dark energy's push. Where matter is sparse, dark energy governs the dynamics. Voids represent environments where dark energy is dominant. With below-average matter density, gravitational forces weaken. Dark energy's accelerating effect meets less resistance. Inside voids, space expands faster than in dense regions. This differential expansion rate creates the peculiar velocity patterns observed in galaxy surveys. Matter flows from voids toward filaments not because voids actively push it, but because dark energy more effectively accelerates expansion where resistance is weak. Although the resulting dynamics resemble a push, the underlying mechanism is independent of matter distribution. The shape evolution of voids provides insights into dark energy properties. If dark energy density remains constant over time, as the cosmological constant model assumes, voids should expand at rates matching specific predictions. If dark energy density changes over time or varies by environment, void expansion will diverge. Measuring void shapes across cosmic history serves to test these scenarios.
DESI's recent observations contain data pointing to possible temporal variations in dark energy density. Statistical significance remains modest and alternative explanations exist, but if confirmed, this would rewrite cosmology textbooks just as fundamentally as the discovery of dark energy itself in the late 1990s. Inside voids, dark energy influences galaxy evolution in subtle ways. Galaxies forming in low-density environments encounter less gravitational harassment from neighbors. They avoid the frequent close encounters that strip away gas or trigger starburst episodes. This solitude allows void galaxies to evolve more quietly than their counterparts in dense regions. Gas reserves remain undisturbed. Star formation proceeds at steady, moderate rates rather than in cycles of violent bursts followed by quenching. Galaxies retain their spiral structures and continue growing in mass, while their cousins in clusters, having already exhausted their fuel, ceased growing long ago.
The Milky Way and Andromeda, both spiral galaxies rich in gas and hosting young stars, fit this profile precisely. Our location in a low-density region may have influenced our galaxy type and evolutionary history. The nature of dark energy continues to be one of cosmology's deepest mysteries. Whether it represents Einstein's cosmological constant, a dynamic field, a modified form of gravity, or something else entirely, cannot yet be determined from available data. Voids offer natural laboratories for studying dark energy in isolation from the gravitational effects of matter. Future surveys measuring void properties across cosmic time will constrain dark energy models.
The void surrounding us creates measurement challenges while simultaneously offering unique opportunities. We live in a place where darkness is dominant, where cosmic acceleration proceeds with minimum resistance, where the ultimate fate of the universe is unfolding faster than average, and where our entire galactic neighborhood is receding at speeds most regions will never reach. The local sheet appears as a flattened galaxy distribution, approximately 300 million light-years wide and 50 million light-years thick. It hosts the Milky Way, Andromeda, several dozen dwarf galaxies in the local group, and hundreds of additional galaxies scattered across the region. From our perspective, these galaxies form a wall separating two voids. On one side, the local void, stretching 200 million light-years, and on the other, the larger KBC void, continuing far beyond the reach of our detailed mapping. The sheet represents a boundary layer between drained regions. Recent analyses revealed that the sheet as a whole participates in a coordinated motion. Galaxies across this structure are moving away from the local void's center at an average speed of 160 kilometers per second. This bulk velocity significantly exceeds pure cosmic expansion at the relevant distances. The additional speed comes from gravitational dynamics. Matter inside and near voids feels a net pull toward the denser regions surrounding the void. In the case of the local void, this means being drawn toward the walls and filaments bounding the empty space. The local sheet is precisely one of these boundaries, a boundary formed by matter that has flowed out of the void and accumulated along the edge of the drained region. This phenomenon repeats itself throughout the universe wherever voids exist. Observations of distant voids display similar patterns, galaxy concentrations framing void boundaries.
The local group itself is moving through space at approximately 370 kilometers per second relative to the cosmic microwave background rest frame. This motion combines multiple components: the local sheet's flight from the local void, the outward flow of the larger KBC void, the gravitational pull toward the Shapley concentration, a massive galaxy cluster several 100 million light-years away, and the negative influence of the dipole repeller, a low-density region on the opposite side of the sky. Distinguishing these components from one another requires detailed modeling of the surrounding matter distribution and gravitational forces. The existence of nested structures, voids within voids, walls within voids, reflects the hierarchical nature of cosmic structure formation. Density fluctuations in the early universe emerged simultaneously across all scales. Smaller overdensities and underdensities clustered within larger ones. As structure evolved, this hierarchy became more pronounced. The smallest bound structures, such as galaxies, formed first. Larger structures, such as clusters, took shape later through mergers. Voids, however, grew primarily through evacuation rather than merging. The result was a cosmic web with features spanning 6 orders of magnitude, from individual galaxy groups to supervoids. We inhabit multiple layers of this hierarchy simultaneously: members of the local group, residents of the local sheet, occupants of the KBC void, citizens of the Laniakea supercluster flow. And at every scale, strange things await us. Beyond the boundary of the KBC void, gravity strengthens dramatically. The Shapley concentration lies approximately 650 million light-years from Earth and represents one of the most massive structures in the nearby universe.
This supercluster hosts more than 8,000 galaxies concentrated within a region approximately 300 million light-years wide. Its mass exceeds 10,000 trillion times that of our own star. Shapley's gravitational pull affects everything within its reach, including our local group. We are accelerating toward it at 400 kilometers per second.
On the opposite side of the sky, something else shapes our motion in equal measure. The dipole repeller occupies a region at roughly the same distance as Shapley. Yehuda Hoffman and colleagues at the Hebrew University identified this structure in 2017 using galaxy surveys and peculiar velocity measurements. Unlike Shapley, the region hosts far fewer galaxies than average cosmic density. It represents another void comparable in size to the one surrounding us. Its name is somewhat misleading. It does not actively push, it simply cannot pull as strongly as the matter surrounding it. The combined effect of these structures creates a dipole pattern in our motion. As we fall toward Shapley, the gravitational braking coming from the repeller's direction also weakens. The effect amplifies our speed beyond what either structure could produce alone. Think of it as rolling downhill while also being pushed from behind. The gravitational landscape of our cosmic neighborhood channels galaxy motions in preferred directions. Caught between an attractor and a void, we are traveling along one of these cosmic highways. Mapping the boundary between the void's interior and normal density space continues to present challenges. The transition is not sharp but gradual. Matter density increases steadily with distance from the void's center until it reaches the cosmic average after several 100 million light-years. Complex dynamics emerge in this transition zone. Some regions host galaxy filaments extending into void space. Others display walls that define the void's boundary. Recent studies used weak gravitational lensing to directly map the matter distribution around voids. When light from distant galaxies passes near a void, the low-density region creates less gravitational deflection than average space. By measuring small distortions in galaxy shapes across large areas of sky, astronomers can infer the foreground matter distribution, including voids. Early results confirm the existence of large underdense regions. The void boundary represents something beyond a geographical feature. It marks a phase transition in cosmic dynamics. Inside the void, expansion is dominant. Dark energy accelerates space beyond what gravity can counteract, and matter flows outward in consistent bulk flows. Outside the void, gravitational attraction is dominant. Matter flows along filaments toward overdense regions. The Milky Way sits somewhere between these two regimes, experiencing the influence of both simultaneously. We live on a boundary in more than one sense, geographically close to the void's center, yet dynamically influenced by the attractors outside. And this extreme environment affects what grows here in ways we are only beginning to understand. Galaxies in voids behave strangely. Observations across multiple void examples reveal a consistent pattern. Void galaxies form stars at higher rates than their counterparts in normal density environments. They appear younger, bluer, and more actively building their stellar populations. This finding has been confirmed and is counterintuitive at first glance. Voids contain less gas and fewer resources. By straightforward reasoning, the galaxies there would be expected to struggle, not thrive. Yet they exceed expectations on multiple metrics. The explanation involves environmental effects. In dense regions, such as galaxy clusters, interactions between galaxies occur frequently. When two galaxies pass close to each other, their mutual gravity disrupts both structures. Gas is stripped away by tidal forces and ram pressure. Close encounters can trigger intense star formation bursts that rapidly exhaust available gas. Major mergers between galaxies create elliptical systems that have burned through their fuel. The result is galaxy populations dominated by old, red, passive systems whose star formation ended billions of years ago. Void galaxies avoid these violent interactions. Separated from neighbors by enormous distances, they evolve in relative isolation. Gas reserves remain undisturbed. Star formation proceeds at steady, moderate rates rather than in cycles of violent bursts followed by quenching. Galaxies retain their spiral structures with ongoing star formation in rotating disks. They appear younger because they genuinely are younger, continuing to grow in mass while their cousins in dense environments stopped growing long ago.
This phenomenon extends to galaxy morphology as well. Void samples contain a higher proportion of late-type spiral and irregular galaxies compared to field samples. Early-type elliptical galaxies that dominate clusters are rarely seen in voids. The morphology-density relation, which describes how galaxy types correlate with environment, displays clear trends. Dense environments host passive ellipticals. Intermediate density environments contain a mixed population. Voids preserve active spirals. The Milky Way fits this pattern perfectly, a late-type spiral evolving quietly in a low-density environment with ongoing star formation. Chemical composition varies as well. Void galaxies display on average a slightly lower abundance of heavy elements. Heavy elements form through nuclear fusion inside stars and are dispersed into space by supernova explosions. Galaxies that have been forming stars for longer accumulate more heavy elements. The low metallicity of void galaxies points to younger stellar populations with a less cumulative star formation history. This makes sense given their evolutionary paths. Without major mergers that contribute enriched gas from other galaxies, void systems build their chemical complexity gradually through internal processes alone. Some researchers suggest that void galaxies offer windows into earlier cosmic epochs. Because they evolve more slowly and interact less frequently, they may preserve the characteristics of younger galaxies across cosmic history. From this perspective, our location in a void does not make us special. It makes us a typical example of an earlier era. We live in a pocket where time flows differently, where the universe continues at its older tempo while the rest of it moves on. Space is not empty. Even in the deepest voids, invisible fields traverse the darkness. Intergalactic magnetic fields extend throughout cosmic structure, having formed in the earliest moments of the universe or accumulated over time through astrophysical processes. The strength and structure of these fields reveal fundamental physics. Voids offer unique environments for studying these fields where other contaminating influences are minimized. With fewer galaxies and less plasma, the primordial magnetic component stands out more clearly. Observations of gamma-ray bursts and distant blazars provided the first clues. These extremely energetic objects emit high-energy photons that travel billions of light-years before reaching Earth. During their journey, the photons occasionally interact with the intergalactic magnetic field. This interaction converts gamma rays into electron-positron pairs, which then interact with cosmic microwave background photons to create new gamma rays traveling in slightly different directions. This cascade process depends on magnetic field strength and geometry. By measuring how much gamma ray emission is deflected or absorbed, astronomers can infer field properties along the line of sight. A 2015 study examined blazars whose light passed through known voids. The analysis concluded that intergalactic space contains magnetic fields of at least 10 to the -7th Gauss. Confirmed through analysis of gamma-ray spectra, this measurement represents an extraordinarily weak field by terrestrial standards. Earth's magnetic field is approximately half a Gauss. The intergalactic field is 100 million billion times weaker. Yet its existence carries profound implications.
Fields this weak cannot easily be produced by astrophysical processes such as supernova explosions or active galactic nuclei. The fields appear too widely distributed and too uniform. They most likely carry traces of primordial magnetism left over from immediately after the Big Bang.
The intrinsic structure of magnetic fields in voids differs from those in filaments. Observations indicate that void fields are more randomly aligned, while filament fields display preferred orientations along the filament axis. This pattern makes sense given the history of structure formation. As matter transferred from voids to filaments, it carried magnetic fields along with it. The shearing and stretching motion of plasma flows amplified the fields along the directions of flow. Inside voids, where flows are weaker and more isotropic, the fields retained more of their primordial random configuration. Theories of primordial magnetogenesis propose various mechanisms for producing cosmic magnetic fields. Some emphasize phase transitions in the early universe when electromagnetic and weak nuclear forces separated.
Others argue that quantum fluctuations during inflation, much like density fluctuations, were stretched to macroscopic scales. The resulting field strength and structure depend sensitively on when and how formation occurred. Void observations constrain these models by providing measurements from the least processed environments in the universe. Whatever mechanism created cosmic magnetism, it operated throughout all of space, including regions that would later become voids. The existence of intergalactic magnetic fields influences many astrophysical processes. It affects cosmic ray propagation by deflecting charged particles across enormous distances. It can seed magnetic fields in newly forming galaxies by providing an initial flux to be amplified by galactic dynamos. It alters the thermal and ionization structure of the intergalactic medium, potentially influencing how the universe reionized after the cosmic dark ages. All of this is another example of how voids, despite appearing empty, harbor structure and information from cosmic history. The darkness conceals something beyond absence. It preserves primordial signals that denser regions have erased.
The cosmic microwave background appears remarkably uniform. Temperature varies across the sky by only 1 part in 100,000. Within these small fluctuations, one feature stands out. The cold spot in the constellation Eridanus is approximately 5 degrees wide and roughly 70 microkelvin colder than its surroundings. The Wilkinson Microwave Anisotropy Probe detected it clearly in 2005. The Planck satellite confirmed it with higher precision. The statistical significance of the anomaly continues to be debated, but the majority of analyses conclude that it is rather unlikely to have arisen from random fluctuations in a perfectly smooth universe. Various explanations have been proposed. The cold spot may represent a rare but possible fluctuation in the primordial quantum field. Standard inflation predicts nearly Gaussian random fluctuations. Gaussianity allows room for extreme deviations on occasion. The cold spot may be a cosmic coincidence with no deeper physical meaning. Alternatively, it may point to non-Gaussianity in the primordial fluctuation field, implying that inflation operated differently from what the simplest models predict. This possibility excites theorists because it would reveal new physics in the universe's first moments. A third explanation invokes large-scale structure along the line of sight. The integrated Sachs-Wolf effect predicts that photons passing through voids lose energy, while those passing through overdensities gain it. It arises from space expanding differently in different environments. Photons climbing out of potential wells lose energy, while those falling into wells gain it. In a dark energy-dominated universe, voids produce a net energy loss. An extraordinarily large supervoid between Earth and the cosmic microwave background emission surface could cool the photons passing through it, creating a cold spot visible in the microwave background.
The search for such a supervoid yielded mixed results. Some studies reported detecting a low-density region approximately 1 billion light-years away, aligned with the direction of the cold spot. The KBC void partially overlaps with this region. Other studies did not find an underdensity pronounced enough to fully explain the cold spot through the integrated Sachs-Wolfe effect alone. The debate continues. What is clear is this: explaining the cold spot most likely requires more than one contributing factor. A moderately sized void combined with a somewhat rare primordial fluctuation may together produce the observed signal. Neither alone is sufficient, but together they create the anomaly. The cold spot represents one of several tensions between cosmic microwave background observations and standard cosmological predictions. Others include a slight asymmetry between the northern and southern sky, unusual alignments of large-scale fluctuations, and a power deficit at the largest angular scales. Some researchers regard these as signs of new physics. Others interpret them as statistical coincidences that appear meaningful when a limited area of sky is analyzed. If the cold spot genuinely carries the imprint of a supervoid, it provides additional evidence that extremely large, low-density regions exist throughout the universe. The KBC void surrounding us would then not be unique. Structures of this kind may be ordinary features of cosmic structure formation rather than rare anomalies. The Boötes void stretches 330 million light-years wide, lying 700 million light-years from Earth. When it was discovered in 1981, it contained only 8 galaxies where 2,000 should have been. Later deep observations raised that count to approximately 60, still catastrophically below average. The void has a roughly spherical shape and stands out sharply against the surrounding structure. What makes it remarkable beyond its size is that its extraordinary depth is surrounded by normal density space without any obvious reason.
The giant void is approximately 1.3 billion light-years wide and lies 1.5 billion light-years away. Its existence at such a great distance shows that large voids formed not only in our local neighborhood, but throughout cosmic history. The CMB cold spot supervoid, if confirmed, is approximately 1 billion light-years wide. Beyond these, the Eridanus supervoid, the Sculptor void, the Capricorn void, and thousands more fill every corner of the universe. Cosmic void catalogs now contain thousands of identified structures, and estimates suggest they occupy approximately 70% of cosmic volume. The Dark Energy Spectroscopic Instrument, which began operations at Kitt Peak National Observatory in 2021, aims to measure the redshifts of 40 million galaxies and quasars within 5 years, creating the most detailed three-dimensional map of cosmic structure ever attempted. Early DESI results, published in 2025, revealed striking clues. Baryon acoustic oscillation measurements showed subtle deviations from standard cosmology predictions at specific redshifts. Whether these deviations point to local structure effects or represent the first evidence of dark energy density changing over time, the coming years will tell. The Euclid Space Telescope, launched by the European Space Agency in 2023, provides complementary observations. Euclid maps galaxy distribution across wide areas of sky and measures weak gravitational lensing, enabling direct measurement of the total matter distribution, including dark matter. The Nancy Grace Roman Space Telescope, which NASA plans to launch in the late 2020s, will map hundreds of millions of galaxies with precise distance measurements and detect faint small galaxies inside voids. The Vera-Rubin Observatory, which began operations in 2025, will repeatedly photograph the entire southern sky, enabling direct local expansion rate measurements based on supernovae in void galaxies.
Dark matter constitutes 27% of the universe. This invisible matter is required by numerous observations, including galaxy rotation curves, gravitational lensing, the cosmic microwave background, and large-scale structure formation. The KBC void challenges standard dark matter cosmology on two fronts. Producing a void of this size in the standard lambda CDM model appears extremely difficult, and explaining the Hubble tension through void dynamics requires enhanced structure growth that standard cosmology cannot produce. Modified gravity theories address both problems. Structure develops faster than in the standard model, voids become deeper, and filaments grow denser. The Milky Way's separation from neighboring galaxies by enormous distances affects cosmic ray flux, intergalactic medium properties, and merger rates, all of which shape conditions for planet formation and biological evolution. Cosmic rays are primarily high-energy particles accelerated to near light speed by supernova explosions. Galaxies in dense regions produce more intense star formation and therefore higher cosmic ray flux. The calmer environments of void galaxies may support surface habitability. On the other hand, void galaxies accumulate heavy elements more slowly, meaning rocky planets emerge later. Whether this is favorable or unfavorable for habitable worlds remains an unanswered question. Dark energy accelerates expansion everywhere. In voids where matter density remains below average, this acceleration proceeds with less gravitational resistance. Over time, structures near voids recede at ever-increasing speeds, eventually crossing the cosmic horizon and becoming invisible. This scenario represents the ultimate fate of all cosmic structure in a dark energy-dominated cosmos.
The Milky Way and Andromeda will merge approximately 3 to 5 billion years from now. The resulting structure will remain gravitationally bound, but the vast majority of other galaxies in the observable universe will accelerate beyond our cosmic horizon. The universe will appear to be emptying from our perspective, resembling the void we already inhabit, but in a far more extreme version of it. Star formation will end as remaining gas is exhausted. Within approximately 100 trillion years, the last stars will die. The universe will enter a degenerate era containing white dwarfs, neutron stars, and black holes. Black holes will slowly evaporate through Hawking radiation. Eventually, nothing will remain but a cold, dark, nearly empty expanding space approaching maximum entropy. Heat death, the ultimate fate of the cosmos. General relativity predicts that time flows at different rates depending on gravitational potential. GPS satellites must constantly correct for this effect. In voids where matter is sparse, clocks run faster compared to the cosmic average. The effect remains small on human timescales. Over billions of years, however, it accumulates significantly. When the universe was 1 billion years old, a clock placed at the center of the KBC void would have run approximately 10 to 20 million years ahead of its equivalent in a dense galaxy cluster today. This affects how astronomers interpret observations. Our local measurements have accumulated slightly more cosmic time. String theory proposes that reality contains extra-spatial dimensions curled up at scales too small to observe directly. Some theoretical work investigates whether large-scale structure formation interacts with the geometry of these extra dimensions. The vacuum state in voids may show subtle differences from that in dense regions, meaning physics would vary by location. No evidence of fundamental constants varying across the universe has been found so far,
However, the searches continue.
Every observation points to a single conclusion that cosmologists are reluctant to fully confront. The universe appears to harbor structure at scales approaching or exceeding the limits of validity of the cosmological principle. The cosmological principle predicts that matter is evenly distributed at sufficiently large scales and forms the foundation of the standard cosmological model. The KBC void stretches across 2 billion light-years. The observable universe spans 46 billion light-years in radius. If voids are this large, the universe may be dominated by low-density regions where filaments form relatively rare features. The assumption of a smooth universe may be more of a prediction than an observation. Reality may be far more uneven. Our location near the center of a large void also raises anthropic questions. Given that observers require galaxies, one would expect to find ourselves not at void centers, but at their edges or in filaments. Yet here we are. The isolation of the void may offer protection from cosmic catastrophes that affect denser regions. The stable evolution within voids may provide better conditions than the violent interactions in clusters. What James Webb has revealed is not only the void surrounding us, it also shows where any observation point under dark energy dominance will ultimately evolve. Isolated, expanding, draining. The universe is becoming what we already inhabit, and there is no escaping without perishing from what we have always been inside. Good night.